Uh, I am going to speak today about exploratory data analysis, and we're going to build up on what we talked about previously, and we'll also look at how to set up your RStudio. So Glory, do you have your RStudio set up? Have you downloaded RStudio? And Devyani, have you guys downloaded and set up RStudio? Okay, Devyani, are you here? All right, excellent. So we'll do that today as well. And we'll also take a look at exploratory data analysis. So we'll play around a little bit with the data. Let's kind of remember where we were. Okay, so I see some more people are joining. So let's remember where we were last time. We'll talk today about how to use data visualization to really understand what's in our data and compare different samples, different genes, and understand what we can do to visualize this data properly. So as you remember, we have the table of expression. Just using this for now. After this, I'll show you how you can do the exact same thing if you have prepared the table of mutation variants as well. So the table of expression, what's important about it are three things. So the first one is that you have column names, and these are your samples. And the samples obviously could be organized by condition. So let me ask you a question. When we look at the 15 gene data set or the 1,000 gene data set that we dealt with last time, what are the names of columns? What are some of the conditions that we have? Who can remember what we are dealing with? Does anyone remember what are the names of columns and what they mean? So let's take a look really quickly. If you take a look with me on this example, okay, so I'll just paste this here. What are these names? So the question is, again, we want to, okay, sample names, but what do they represent? I mean, obviously, normal-like, basal, 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 right? These are not really sample names. Sample names would be sample 1, sample 2. Okay. Expression, well, the expression are the numbers, right? So expression is like heat. You can measure how hot something is. So this is the expression. But what are these names? What do they mean? Normal-like and normal-like. What might this represent? Does anyone have any idea of what this might be? Okay, so what this represents is a subtype of cancer. So we can call it a condition or a disease. So this is multiple samples. And based on this annotation, we know what group they belong to. So this is like a grouping of our samples, okay? So this is the first important thing to remember, that in our table, remember that we have names of our columns, and that's the header. We have the names of our genes, and here for simplicity, we have gene 1, gene 2, gene 3, etc. So these are different genes. There's a total of 15 genes and a total of 52 samples. But there's only a few groups out of these samples. And so when we look at this table, we have the sample name, we have the gene name, and this is the expression level, right? So in the intersection inside our cells is the expression level. And last time we talked about how this is numeric data, and that is our matrix. And these are not included in the matrix, right? So we want, when we do all kinds of visualization and analysis, we deal with the numeric data, and we keep somewhere the annotation for what's in our data set so that we can deal with it more easily. Okay, so let's try and look at how we can do that together. I'm just going to delete this. Okay. Let's start. All right, so cleared up everything. Okay, so please go with me to the playground for now, and then we will try to go over to our studio today as well. So once you're here, let me know. Okay, so once you've arrived at the playground, just put in 1 or I'm here or yes or something like that. Oh yes, sorry, you don't have access to the playground. Okay. So since you don't have access to the playground, let me do this. Okay, so let me do this in, we were introduction to data science, and we have our data visualization section here. So let's just open the try it yourself section. We can just open this last one, and we can do it right here. Okay, so if you could go to this course, and we'll just try to first do everything in here. Okay, so let me know once you're there. All right, excellent. So please, for the rest of you, all right, great. Emeka is also here. All right, so the first thing that we want to do is we actually want to load in this table, right? So to load this table in, we have it right here. Let's go ahead and create an object, right? So this object is going to be expression table. So we don't forget what this is. So expression table, and I can see right here I have read table, right? So read table, and include the file that I gave you guys. And so the file is this one. Now, as you remember last time, we talked about how we can set the header to be true and row names to be 1, right? Because we have here our names of columns, and then we have row names. So just to make sure that this has loaded in correctly, we can do, what is the function for me to see the first 10 rows of the data set? Head. All right, great. So let's do that. So head, expression, table. Let's run that. Okay, so here we have our data, and we can see that we have normal like 1, basal 1, basal 2, etc. So it shows us all of this data. So the data has loaded correctly. But if I want to do something with this table, right? So for example, if I want to do a box plot expression table, okay, one of the things that I don't want to have is I don't want to confuse myself with the names of these columns, and it will also help me understand actually what is the what are the different levels that I have. So what are these different conditions that I have down here, instead of relying on this just looking at all of my data as strings, right? So one of the things that I want to do is I want to convert the names of my column names, convert them to factors, okay? So here I'm going to say strings as factor equals true. And the other thing that I want to do is I want to save these names. So I can do sample names, create an object, and create as factor. And here I'll take call names from the expression table. Okay, so let's forget about this for a second, and we'll just print sample names. Okay, so what do we see here? Here we see that we have 52 levels, which is the 52 samples. So just adding here strings as factor is not enough. The other thing that we want to do before that is to disable checking the names. So we can just do check names equals false, false. Okay, let's try this again. Okay, so now we see here that we only have 4 conditions: basal, cloud and low, luminal, and normal light. So our names don't have the numbers anymore. The names of our columns don't have any numbers. And now it recognizes that when it says luminal multiple times, it actually is going to be displaying a single type, but 4 times, multiple times. Okay, did everyone manage to see the same thing? And I can just share with you. Okay, great. So I'll just share with you the code in case you want to repeat this. Okay, and let me know if you get the same thing. So the important part here is to see that you only have 4 levels instead of 52. Okay, did anyone else get this result? All right, great. Glory, Susanna, anyone else? Okay, so wouldn't it be nice now to make a box plot for this, but instead of looking at everything being gray, making it colored by type, right? So how would we do that? How would we add color to this box plot? Who remembers how to add color to the box plot? Does anyone remember how to add color? To add color, all we need to do is we need to say here col, right? Okay, great. So Susanna, it looks like you have ID. Where is ID? Let's look. So ID is this row. So what you probably forgot is this little piece of information, which is row names equals 1. So you can see that here, after I do all of this, I say row names equals 1. All right, so try that again. Okay, so if I do color and I assign my color to be sample names, what will I get? Let's take a look at whether what we are getting here is correct. Okay, so first of all, we don't have all the names. So let's add here last equals 2. So now we see, okay, so Normalike is blue, Basil is black, right? Basil is black, Luminal is green, Basil is black, right? So now we have our colors according to type. Is everyone getting this? Or is anyone getting this? All right, Gloria is getting it. All right, great. So if anyone else needs me to pause and you're getting errors or something like that, let me know. Okay, so but the black color here is kind of ugly, right? So how do I actually specify what colors could these be? One way to do this is to create a number of colors from the rainbow palette. So I can just say that since I know, and I don't need this anymore. So since I know that I have 4 colors, I can say colors, or my colors, let's call this my colors. And I will say rainbow, which will give 4 colors out of the rainbow palette. Okay, and then here I can set a palette. So palette, and that would be my colors. So let's try to run this. Okay, not rainbox, rainbow. Okay, so now I have some more interesting colors. So I've got my rainbow colors, right? And I have all the luminal are now this nice. Now the problem is that also this at the bottom is being cut off, and I don't like that. And you can also see that now my names don't have any numbers after them. So let's add a little bit of padding. So the way to add padding, so let's do set plot, or plot settings. We'll call this section plot settings. So here I can add par. Margins are going to be, and here I have 4 margins. So I can say, for example, 10, 10, 10, 10. Let's try that. Okay, so now I have a bunch more space. Maybe I don't need so much on top, but at least I have here a bunch. Okay, so and now I don't have even enough space. So maybe 10, 10, 10 is too much. Let's try to reduce it. Okay, so this reduces it at the bottom. That's something actually I do need. Let's play around with this. Okay, so now I remove this one. That's good. Probably need to remove this one also, and this one also. Let's try that. All right, great. So now I've got a nice looking plot. Okay, sorry, Yermak. All right, so now we have a nice looking plot, right? We have our margin set up, we have our color set up, we have our names correctly showing up, right? So everything is looking good. So how do we apply this information, right? So we've got here this nice plot. How do we understand what is different between these different samples, right? So just by looking at this example, when we look at this bar plot, we know that we have some statistical properties shown here, right? So for example, we have the mean, the interquartile range, we have our maximum and minimum, And we can see some variation here, but maybe it's not so clear just by looking at it like this. And one of the reasons is because it's not organized, right? So all of my groups are kind of spread between each other. So the final thing that we'll do in this exercise is just to organize our information. And so the way that we organize things is we can use two different functions, one called sort and another one called order. So the first thing that we need to sort is the actual expression table, right? To sort an expression table, what is an expression table? What kind of an object is it? Okay, and sorry, Susanna. No, we do not need to apply log transformation because you can see that it is already spread out, right? If it was all at the bottom, we would use the log transformation, but this is already log transformed. We'll do this in a second with this other data set just to understand. But can you tell me what kind of an object is expression table? Is it a string? Is it an array? Okay, data frame, right? So it's a matrix or a data frame. So it's got both rows and columns and a bunch of values in between. So to work with a data frame and organize it, we use the order function. So to do that, we will say expression table, and we will put everything back in it. But first of all, we will say order like this, and then we'll say by call names. Yeah, so we have the column names, call names of expression table. So now we will have them organized by the column name. So let's try to run this, okay, and see what happens. So what happens? All of our samples got organized, right? So they are, normal likes are here, luminals are here, right? Cloud and lows are here, so all of them are organized. The problem is that the colors didn't get organized, right? So now to organize our colors, which is in this object, my colors, we use the sort option or the sort function. So now we need to say that my colors sort, well, actually not my colors, sorry, sample names, right? So sample names, sort, sample names. Let's run this. What happened here? Sample names, sort sample names. As factor, okay, sample names. What we probably, okay, so probably the reason for this is because we're doing this here. Let's try it like this. There we go. Okay, so we first want to sort the sample names, then we want to organize our expression table. All right, so here now we have our samples organized. Did everyone get the same result? Or does anyone have any questions about how to get the same result? Okay, yeah. So let's go through. So first of all, we load data. Then assign column names to an object. Then we sort that object. Okay, then we actually then we'll do sorting. Then assign colors. So I guess we can put this under our plot settings. And create a box plot, so visualization. All right, great. So we have Glory and Susanna that got the same results. Let's just make sure that everybody else also has the same results. Okay, great. So kind of similarly, the important thing is that it worked, right? So did anyone else get this working for them? Now, looking at this data, what can we say about our samples? Okay, so the median lines are not in the same. That's interesting. Maybe you can share with us what, you know, for example, your code, and we'll take a look at that. So let's see here, based on what we are seeing on the screen, what do we actually understand about the differences between these samples? So the samples for basal, their median line is right around between 4 and 6, right? So here we have our median line between 4 and 6, as opposed to cloud and low, that is more like between 0 and 2, right? So we can say that overall, based on this 15 gene data, basal are upregulated on average compared to cloud and low. We can also say that luminal also stand out, right? And so luminal samples also have a higher expression overall. We also know this because the maximum for luminal is higher. And we can also say that normal-like are probably a lot like basal, right? So they do look kind of similar to basal. So what this transformation of data, organization of data, and visualization of data helps us understand is, what does this data describe? Okay, so just so that your sorting is correct, make sure that you are sorting your expression table after you sort the sample names. Okay, so this is what you can do for sorting. All right, great. All right, does anyone have any questions about this? Okay, no questions. What other visualization do we know that can help us understand differences and compare different samples here, right? So for example, we know that cloud and low are different from basal. Could we take a sample from basal and a sample from cloud and low and compare them? What kind of a comparison would you do? So how would you compare a basal sample, let's say sample number 1, and clouded sample? How would you compare those two? Yep, we can use heat maps. So let's try heat maps. What other ideas do you have? Scatter plot. Okay, so Susanna, what kind of a scatter plot? What would you be using as your y-axis and as your x-axis in a scatter plot. And any other ideas are also welcome. Okay, so expression level for y, and what would be on your x-axis? Okay, so what would be the difference between x and y? So x and y would be the same thing? Okay, well, the answer is that you would probably want to take expression levels from one sample to be your x-axis and another sample to be your y-axis. So let's try that first, okay? Before we do, if we do, just plot, okay? And put in expression table, okay? So just like that. What are we going to get? Okay, we cannot do that. Okay, so let's make sure that when we do this, we actually have a matrix. Okay, so first of all, let us create a matrix. So let's create expression matrix as matrix expression table and do expression matrix. All right, what are we getting here? So we're getting something strange here, right? When we do this expression matrix, it shows us Basel and some lines here or some dots here. To really look at all of our data, okay, do I need to do as data frame? Okay. Let's not do this anymore, and let's not do this. Expression matrix as data frame. One second, something I'm doing here is not correct. Okay, one sec, let me figure out. As matrix, expression table. Okay, but what I'm supposed to be getting is actually all of my data, right? So, okay, well, let's try this. Let's do expression matrix. So here we can say, let's say, normal like. What is it exactly called? Normal like. Normal like. And we can take luminal. expression table. Like, okay, so let's do this then. We'll do 1, and we will do 6. Okay, what does it now like now? So this is our X and this is our Y. Let's try this. Okay. Okay. So yeah, so now we have expression table 1 and 6. Okay, so in this plot, we are comparing these two samples, and let's just see how many dots do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Because this has 15 genes. Okay, so you can see that the last one is 15 genes. So what we have plotted here is a comparison between the first sample and the sixth sample, right? So here, let's just do the box plot, and we'll see which ones we have. Okay, so the first one is basal, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's do 14. Okay, so instead of 6, let's do 14 like this. Okay, so here we have our x-axis and y-axis, right? So here we have our first sample, which is a basal one, and here we have the 14th sample, which is cloud and low. So if I have those two, how do I know that they compare to each other well or not well, right? Allison, yes, we can from the admin side, but yeah, we can install all of the packages. Okay, so here we have a comparison, right? The objective of this is to explore whether these two samples are comparable, right? So when we have a scatter plot, we can plot two axes and organize them to either compare our samples to each other or genes to each other. The problem is that if I want to compare all of my samples between each other in a scatter plot, I cannot just do it like this, right? So this scatter plot actually does not allow me to do that. Instead, I can compress the dimensionality of all of my data into just two major components or dimensions that will allow me to visualize how all of the information that we have can be visualized in a scatter plot. And the way to do that is to use a function that will represent a scatter plot, right? And that's called principal component analysis. So after we do this plot comparison between two samples, let's run a principal component analysis and visualize all of our samples in a scatter plot. Okay, so let's delete this. And let us do PCA. And here we will run a PRComp. So PRComp. And we will analyze our data set. So here we can have, and by the way, we will need to install here a library. Okay, so the library that we will need is called GG45. Okay, so here we can actually say library ggfortify, and we will do pure comp of expression table. And now we can plot this using autoplot PCA. Okay, so let's try running this. Okay, so we have a scatter plot, but what does this scatter plot tell us about our data? So first of all, we have here, just count the number of items that you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, okay? So 15, what is 15 in our data set? Do we have 15 samples? Do we have 15 genes? Which one is it? Genes, right? So what we're seeing is a scatter plot of genes, and the dots represent genes, and it somehow is showing us how are these genes different between samples. But that's not what we want, right? What we want is to analyze samples based on all of our genes. So to do that, all we need to do is we need to transpose our table. So let's transpose our table. How do we do that? Let's create a new object. So we'll call this expression T for transpose. And here we just say T expression table. Now, instead of using expression table, we will use expression T. Let's try that. All right. So now I can see that there's many more, right? So not 15 anymore. And I'm starting to see here pretty well-defined groups. So if I had the colors, right, if I could color them, I could probably have a good sense of which groups they are. Why did we need to transpose? Okay, so principal component analysis looks at variance in your data frame based on your objects and features. When we look at objects, those are typically what we've done up until now is we've looked at objects being our columns. But PCA looks at objects as rows. And so when we will do all of our exercises next week, when we do all the clustering and classification and other machine learning algorithms, they typically look at a table sideways. So sideways means that instead of your columns being objects, it's looking at objects being your rows. So to make our table prepared for this analysis, we just need to flip it. And transposing really just means you flip it on the side. So instead of your header representing your samples, now it's representing your genes. And instead of rows representing your genes, it's now representing your samples. Okay, just because this is how PCA and clustering and many of these work. Okay, so just to make sure that everyone is following along, was everyone able to add these few lines of code and visualize this scatter plot based on principal component analysis? Okay. All right, excellent. So now let's add some colors to this information here. So autoplot, let's add labels. And let's see what happens. Okay, so it added here some labels and we see what the names are, right? So we have here luminal, basal, normal-like, and cloud and low. What else can we do here? We can actually add color, right? So when we have our object, we can try and look at colors. Okay, one sec, let me remember exactly how I can add the colors because I don't remember. Is it color? Okay, must be either a length of 1 or the same as the data, so 52 color. Okay, so sample names. Okay, so here we need to do okay, so here I think what we need to do is we need to change, let's see, sample names as factor, numeric. Okay, so we'll do that. So we will say here sample colors. All right. So it did some coloring, but the coloring is again not in order, right? So we have here luminal, there's all kinds of colors. So we do have some colors, but the colors are definitely not matched to what we want. So instead, let's just do rainbow. Like that. Okay, rainbow 52, I believe, is going to give us just all the colors that there are. See what it gives us. Yep, all the colors in the world. Okay, let's see. Forgot how to color them. Let's try to figure this out. Okay, so label. Okay, so a good way to remember is to go to our autoplot. And let's look it up real quick. In fact, we need autoplot. Okay, so in fact, we have autoplot CA. Okay, so here we need to have color. Okay, so by group, so color should be, so color, like this, sample names. Unknown. Okay, honestly, right now, I don't remember how to add the colors here. But the good thing that we have a full lesson already here. And if you follow through this lesson, you'll be able to go through all of these steps and add all of your colors right here in this exercise. Okay, let's see. PCA, okay, data frame. Pure comp. Okay, how do we interpret this PCA plot? So we have here a 2D representation of our data. Okay, let's actually forget about the color really quickly. We've got the label, so we know what's in there. Let's look at what is inside this object. So if we go to print PCA, you can see that, and in fact, you remember that we have this option to write a table, right? So we can, that will be easier for us to understand. So let's do write table. PCA. One sec. Let me get the okay, right table. Okay, PCA result, right? So what I can do, okay, PCA X. Okay, so here I need to do PCA will be PR comp, right? And let's forget about this really quickly. We need to create a new object, PCA res, just the result. And in there, we will take one of our data frame objects. And here we will have, so these are going to be sample. Okay, let's do this. So here we'll do samples. There we go, samples. These will be call names of expression table. Okay, so here we will do samples and PCA, just the X of our PCA. Okay, and here we will do write table, PCA, res, and file PCA txt. So let's try this real quick. Okay, let's take a look at this table to understand what this means. So in fact, we can save this table and see what does it actually represent. Okay, sorry. When we do this, we need to make sure that we have a nice separator mentioned here. So here, T, let's run that again. Okay. So let's see what's inside of this information. Okay, so here, as you can see that previously we had a table that showed us gene name, right? What genes were our rows and samples were the columns. What principal component does is it looks at all of the information that each gene contains, so each one of our characteristics of the sample, and transforms this multidimensional space, which now has 15 dimensions, right? Because we have 15 genes, 15 characteristics for each one of our samples. And we can transform our data so that all of these 15 become principal components. So it reduces from a total of 15, reduces it to the main two that are projections within the space. And now if we take just these two columns and we create a scatter plot, the scatter plot is a projection of all of the 15 onto the two primary components. And these two primary components are the most informative about our data. Okay, does that make sense, Junmei? Okay, so when we have our samples, right, we want to characterize the samples based on the information that we have. The information that we have is the gene expression. So how do we kind of condense all of that information into a simple representation? We do it using principal component analysis. Okay, so here now we have this samples, right? So let's color, I believe. So if we do plot or autoplot PCA, samples, unknown color name, samples. That. Okay, so as factor, let's try that. That will work. Okay, so air, okay, no, known color name samples, normal like, okay. As numeric maybe, as numeric. All right, we got something here, let's see if it worked. No. Okay, so unfortunately, I don't remember how to do the how to actually run the colors, but I will figure it out for next time. But what I wanted to explain here is how we can actually create a scatter plot, right, based on the information that we have, which is the genes. How can we explore those genes, explore those samples based on what we know about uh, our genes. And okay, so that's why. So data equals expression T. Something is wrong here with my code. I'm not sure what. Because it is showing me everything. Okay, so the color is not working. That's the problem. So the color is not working. That's why this is not working. Okay, so the important thing is that we understand that the information that we have in this gene expression can be analyzed from the perspective of samples and from the perspective of genes, which is like this, right? So here we actually see the gene expression information. Here we do not see the gene expression data anymore. This data is compressed, but this view does convert the information about gene expression into a distance. And now we can see distances between our samples, placing some samples closer together. And this distance space now means how they are similar. So distance equals similarity. So now we can think of our data in terms of groups in this hyperdimensional space, right? So hyperdimensional just means that we have more dimension that we can visualize. And so we have this space. In this space defined by the data that we have, we can measure distances. Does that make sense? Because this really leads into our ability to analyze this space using Euclidean distances to infer meaning from a more complex data set that we could simply visualize and study using statistical properties. Okay, so this is a statistic. These are different statistics. And here we are kind of going beyond the individual statistics and looking at a multidimensional space from a perspective that we can understand, that we can interpret, because here we can easily measure distances. Okay, so hopefully most of you were able to follow along. Sorry about the coloring. I'll figure it out for our next session because we do have a hands-on session coming up. So we'll kind of go through all of these exercises together. And for the remainder of today's session, I just wanted to make sure that everyone is comfortable using RStudio. So how many of you here have RStudio installed and ready to run? Okay. All right, so let's open RStudio. Let me know once you guys are ready. And let's do the following. Here you have a copy icon. So you can just copy your code and then paste it right here. Okay, so once you do that, you can just do run. Sorry, that would just run that line. But you can do Command Alt R, okay, which in my case on a Mac, it's Command Alt R. If you're using a Windows, that would be Control Alt R, or you could go to Code and run region, run all. But if you run this whole data set, you will see that all of the same is happening, but instead of in the code playground, you now have all of this information in your RStudio. But there's some additional benefits to doing this in an environment that is set up to help you understand what things are working and what things are not working, so that you can easily understand what's in the different parts of your code. Okay, so how many of you have the same results here? Okay, Susanna. Okay, so here, an additional type of information that we have is all of the objects and all of the data frames that we have. So for example, here I have my values. So for example, I've got new colors. Okay, so new color has a bunch of NAs, and that's why I was getting this bad information. So let's see, sample names is factor with 4 levels, samples, new color. Okay, so new color as numeric samples. So probably like this as factor. Let's try that. Okay, so now I've got it, and now I can add color. Okay, yeah, so you have to install, if you go to tools, you have here install packages, and here you just write ggfortify, and you will come up, and then you do install. Okay, so here, new color. Okay, it's coloring, but incorrectly. Okay, so Susanna, let me know once that works for you. Okay, maybe I know it's because we probably need to do this here. All right, so here. Okay, so I will figure this out for our next session, but basically I think it's because I'm transposing the table. So let's just do labels equals true for now. Okay, we'll run this. And you can also navigate here between all of your data. Now, an important part also is that we are still using here this link. And instead of using this link, we could have used a file that's already on our computer. To do that, however, it's useful to set up your working directory. So if you are in your home, right, so you will be on like My Computer or something like this, you can navigate here to whatever folder you want. And here I have a number of files prepared. So I can just use this as set as working directory. And once I do that, I will be able to get any information that is here. So for example, well, I'll just write it out. I can call this expression genes 1000 cell line. So let's try that. I need to go to that folder and really quickly change the name of that file because it's got a space. Okay, so for example, here I have 1000 cell lines. Okay, cell line expression genes 1000 cell line.txt. Set as working directory. There we go. Okay, so in this example, I have something else, right? A different result. And so you can now start practicing with the different, because here I actually have some less samples. Okay, so if everything is working for you, what I recommend for next time is to please complete a course that we have in the Introduction to Data Science called Advanced Data Visualization. So this will give you some more new exercises that you can go through to do what we did today and to master all of the visualizations, including organizing your box plots by group and making sure that you can run scatter plots to compare different samples. Understanding that log transformation really helps us compare samples from the same condition and also identify differences. So spot differences, this is a scatter plot for all of our data where you can easily see what the heat map idea is, right? So if you see here, you've got samples from the same group, non-malignant versus non-malignant, and they're all tightly aligned to each other. But when you take non-malignant, so these are all non-malignant, versus cloud and low, you can see that how the lines start spreading out. So all of the genes are now not comparable between themselves. So you really understand how the data represents these different groups. And the same, of course, could be said for bar plots. We can use bar plots to visualize our data and compare different conditions. We also talk here about heat maps, how you can visualize heat maps and make sure that you spot trends in heat maps, and how that changes when you start using log scale data. And then here you can also learn about histograms, as well as density plots that allow us to get an overview of how different our samples are overall. And there's also going to be an introduction to ggplot, which is a useful way to do object-oriented visualization. And so here you will find the same plots, but using ggplot. And in the future, this will be useful for us to deal with the different elements within the different packages. Okay, so again, the link is in chat. we covered today a few examples of visualization to understand what's in our data. So this is an advanced visualization, and this is a course on dimensionality reduction and visualization using principal component analysis that you can actually practice the different types of outputs here, including some introduction to clustering and feature selection, which we will talk about in our next session. So any questions about this today? All right, so if there are no questions, please do let me know if you run into any challenges. You can try to run code in here based on these exercises and then copy and paste it over to your RStudio just to make sure that everything works there. And we'll talk next time to kind of go in further and talk about what all of this means and how do we work with other types of data using the same ideas and principles. Thank you again for joining, and I'll see you again next time.